would basically involve the same physics. Now, we did think about the gamma radiation that would be produced during the radioactive decays, and we concluded actually that this radiation would be much too powerful to explain the recently discovered gamma ray bursts, because everybody knew gamma ray bursts were in our galaxy. So instead of turning the argument on its heels and basically saying, these are gamma ray bursts and they must be extragalactic, we punted. So following this, the sort of scenario didn't really achieve much success in terms of people believing that this is really where our process nuclei came from. It's considered very speculative. I think the argument started during my thesis defense. Dave Arnett gave me a particularly hard time. Why, I could be doing real problems. Why was I working on this one? And I have a lot to owe to Dave, actually, because as a first-year student, he wouldn't let me take his hydrodynamics course. And I fear to think what would have happened if I had taken hydrodynamics and become a hydrodynamicist. So I thank him all the time for saving me from that fate. So the first real hydrodynamical calculations, grid-based hydro simulations, were done by Nakamura and Ohara in 1989. Lee and Paczynski wrote an interesting paper, of course, suggesting what we now call macronovae or kilonova, that the electromagnetic signatures of the merger, our process, would be possibly visible. And they estimated the time scales and the fluxes from this. Of course, they didn't have the opacities right, but
you also have the nuclear heating as a free parameter, so their things are much brighter than what we observed.
Okay. Yes. And then the first GR simulations were done by Shibata's group, and also Roswag and Davies, polytropic EOSs. So Roswag and Davies were focused more on polytropic EOSs, but the GR simulations by the Japanese at this time didn't really care about mass ejection or the R process. They were interested in calculating the gravitational radiation signal, and so that's where a lot of the effort in GR simulations stemmed from. And then there were further improved nucleosynthesis calculations involving full networks that basically confirmed that our process material would occur in decompressing a neutron star matter. So there never seems to have been much debate that these would work. They're the perfect site for the R process. The question is how frequently they occurred and how much mass would be ejected. But then calculations showed additional mechanisms for ejecting mass from shocks, from MHD, from neutrino-driven winds. Sort of the whole time, people still thought, though, that supernovae were the real source of the R process, but those simulations were constantly hitting the wall, and in fact, putting in improved neutrino physics seemed to always make the matter worse. That it was very difficult to get sufficiently neutron-rich ejecta from this. And in addition to that, there were real problems with chemical evolution ideas. So in the standard models of chemical evolution that persisted up to maybe 10 years ago, they were similar to closed box calculations, maybe with some inflow, but basically the coordinate that you see here have the logarithm of our process abundances versus the iron to hydrogen ratio relative to the sun. And in these classical chemical evolution models, Fe over H is basically a proxy for time. Supernovae occur constantly at a very high rate from the beginning of the massive stars, and so of course iron builds up steadily with time. The red dots in these pictures are the observations taken from a paper by Argos et al. 2004, and modeling the R process production with supernovae fits the general trend that's observed very well. So the black dots are simulated stars in their chemical evolution models. Neutron star mergers have a problem because there's a significant time delay between the supernova production of neutron stars and their eventual mergers. The time delay could be no shorter probably than 10 million years, and maybe much longer, 100 million years or even a billion years. And so this is a real problem. And Chen and Wasserberg added more fuel to the fire, basically suggesting that neutron star decompression was disfavored because of the energetics and the extensive mixing that would have to occur to explain why such rare events could contaminate an entire galaxy on such short order. So up until 2015, there were many examples of chemical evolution studies that continue to favor supernovae. So the thing that turned the tide, I think, eventually is the work of Prantzos in 2006 that showed that the unique relationship between time and metallicity is destroyed if you accept the modern idea of hierarchical galaxy formation, where basically galaxies form from mergers of small pieces. And so then the observed early appearance of our process elements and their large abundance dispersions in stars could be explained, even if you had large decay times, orbital decay times. And so here's some examples of some simulations by Komiya and Shigeyama. Basically, the points again are the observed our process abundances and iron abundances in our galaxy, and the blue curves and their contours basically show that the models can roughly more easily fit these sorts of observations, and you don't see the extensive appearance of a delay that's really ruining the agreement. But in addition to that, also about 10 years ago, there became interesting connection that appeared between short gamma ray bursts and mergers. There are a lot of observational evidence linking short gamma ray bursts with mergers because of their locations in elliptical galaxies and no associated supernovae. And the Lee and Paczynski picture was partially validated by the discovery of macronovas in perhaps as many as 3 systems, now 4. So the first of these was gamma ray burst 130603, and so from the paper of Tanvir et al., for example, you can see the appearance of the afterglow, which is documented in this one data point. So it's kind of thin evidence, and probably could have multiple explanations, but it is consistent with this ejection picture. But Wallner in 2014 finally was able to get measurements that weren't just upper limits to the abundances of the abundance of plutonium-244 in the crust of the Earth and in sediments on the ocean floor. And these showed that the abundance of plutonium-244, given the current abundances of our process elements in the universe, plutonium-244 is an R-process nuclide, these abundances were actually 100 times lower than you would expect if the R process had occurred continuously by a small yield, high rate event like a supernova. And so Zvi has this nice blackboard demonstration of what happens if you have a rare event with a huge production. More likely than not, if you observe at some particular time, you're going to observe a low abundance. While if the event is frequent with a smaller yield, you will generally see a much larger abundance at any given time. So statistically speaking, this very low abundance of plutonium-244 is inconsistent with the supernova picture and consistent with a rare event, or at least an event that occurs in a supernova but only in a very small fraction of supernovae. So that was interesting. And then there is also the discovery of R process abundances in 1 of 10 ultra-faint dwarf galaxies. Now I think they've been discovered in 2 out of 16 or 17. I don't know what the latest story is, but G et al. Found in their study of 10 ultra-faint dwarf galaxies that only 1 of them had detectable R process abundances, although all these galaxies showed a steady rate of iron production that was a function of their luminosities. So these are dwarf galaxies, and these are ultra-faint dwarf galaxies, and they all are along the same trend, indicating continuous supernova production. But when you look at the European abundance as a proxy for the R process, as a function of luminosity, you find that in the ultra-faint dwarf galaxies, only reticulum-2 had detectable R process. The other ultra-faints didn't have any, and then dwarf galaxies had, followed this general trend. So this was indicative of a very rare high-yield event producing the R process as compared to something with lower yield. And so the idea is that if you plot rate versus ejection, you should get a straight line would give us the observed R process abundance, and whether or not you normalize it compared to the historical rate of R process production or the current rate, you'll follow one of those curves. And if you put then the evidence from plutonium, from ultra-faint dwarf galaxies, from the short GRBs and so on, everything seems to line up along this curve with suggested mass ejection on the range of 100th to 1/10 of a solar mass per event. So the picture's converging very nicely here, and I think all we really needed was the gravity wave event, in which there is an abundance of both blue ejecta and red ejecta, which we've heard a lot about and we'll hear some more about. And so I guess I'm going to talk again for maybe 10 minutes later to give my impressions of what this event means for neutron star structure. But to conclude this particular saga, it's very nice to see that something that was proposed so long ago and got very little recognition. I think everybody knew that the work was done, but it really wasn't accepted as something that was actually happening. So it's very nice for me to see that. Thank you.
Any questions for Jim?
In a neutron star merger where the black hole was 15 or 20 solar masses, how much less ejected mass did you expect?
Well, if the black hole's not spinning, the neutron star will just plunge. And I think modern calculations show that it's the same thing. I think the mass ratio can only be 3 to 5 to have ejection, unless the black hole is spinning. If you spin the black hole close to the maximal rate, then the mass ratio can be very large and still lead to mass ejection. So.
Good.
Why do you see this really large scatter in our process abundances in ultra-faint dwarfs, but not in regular dwarf galaxies?
What do you mean?
I mean, if you go back to the plot you showed before.
Just number.
Just number of stars in there.
You mean this scatter here?
On the
No,
bottom
down
right.
bottom right.
Oh, these are upper limits.
Right. So there's this big
So they only
scatter
are
in the-
observed in one. It means that only one of these 10 galaxies has had a merger. And actually from the stars that were observed, and you can calculate the total abundance of R process elements in reticulum-2, and it's a few hundredths of a solar mass. So there's been one event apparently in that one system that's contaminated all the stars that we see for which the R process has been measured. But in the other 9 ultra-faint dwarfs, there hasn't been a merger, and so there's no R process elements there. So people living in those galaxies don't.
But I
don't
think the other thing is
wet
as you go up you have to worry about North Korea.
What?
You have to worry about North Korea. But I think the other thing is as you go to the more massive ones, you're going to statistically average these things out, right? Because they have many pollution events. And so, any other questions, Jim? If not, let's thank him again. Let's take about a 12-minute break, and then we'll get started with the afternoon.